Its 36-year objective was to boldly travel where no probe had gone before, search for new plasmas and aberrant cosmic rays, and investigate bizarre new worlds. For almost 40 years, Voyager 1 has been exploring space, and during that period, it has exceeded its original objectives. It was predicted that the spacecraft would only last 5 years, yet it has exceeded all predictions. It has now gone a step further. Everything has altered after Voyager 1 discovered unidentified objects moving through space. The galaxy's magnetic field is carried by the plasma, which is the result of huge stars exploding millions of years ago. Come along as we discover what these unidentified objects are and how they could permanently alter the way we view data. We have mostly only examined data from within the solar system for the previous few years, but Voyager 1 has given us access to data from outside the system as well. Voyager 1 officially crossed the heliopause and arrived at the end of the solar system in August 2012. But it wasn't a simple task. The quantity of sunlight available to power Voyager 1's equipment and systems decreased dramatically as it drifted farther away from the Sun. 3 radioisotope thermoelectric generators, RTGs, which transform the heat created by plutonium-238's natural decay into electrical power, provide the majority of the spacecraft's power. The available power has decreased over time as a result of the RTG's declining heat production. The functioning of several systems on board, like as communication capabilities, data transmission, and scientific instruments, is impacted by this power loss. Some non-essential instruments and systems have been put in a dormant or deactivated condition in order to save energy. Critical systems could need to be shut down or further optimized as the power continues to drop in order to prolong Voyager 1's operational life. It may not be as helpful to us if it does continue to function. Another major obstacle to maintaining efficient contact between Voyager 1 and Earth is the great distance between them. The signal power significantly decreased as the spacecraft entered interstellar space, and it currently takes more than 21 hours for signals to reach Earth from Voyager 1. Successful data transmission and reception are significantly hampered by the weak signal and background noise interference. In addition to power problems, there are problems with temperature. Voyager 1 experiences a change in temperature as it moves from the heliosphere to interstellar space. The spacecraft encountered higher temperatures in the heliosphere since it was nearer the Sun. Extremely low temperatures, which can affect the spacecraft's materials, electronic components, and systems, were encountered on its journey into interstellar space. The structural integrity of some parts may be impacted by thermal stress and cycles of thermal expansion and contraction. Seals and connectors may break or deteriorate as a result of materials becoming brittle due to extreme cold. Since the RTGs are made to function within particular thermal ranges, these temperature fluctuations also affect how well they perform. The power problems are made worse by cooling the RTGs, which lowers power production. There is a patchy distribution of dust particles in interstellar space, thus it is not completely empty. Despite their tiny size, these particles have the potential to endanger Voyager 1. The spacecraft's outer surfaces may be impacted by interstellar dust particles, which could erode sensitive sections such as antenna surfaces or protective coatings. Dust buildup on the instrument sensors or optics might impair their performance and reduce the quality of the data. A dust detector equipment on board Voyager 1 was created especially to gauge the density of interstellar dust. Additionally, communication chances are less frequent than previously because to the restricted resources that NASA's Deep Space Network, a global system of antennae for connecting with deep space machines, must devote to receiving Voyager 1 signals. Amidst the deluge of information, an intriguing finding surfaced. A fascinating anomaly was discovered by Voyager 1, a collection of signals, the majority of which were difficult to interpret, but one of which revealed the existence of 300 unidentified objects traveling through the cosmos. Scientists worldwide are baffled by these enigmatic beings that are emerging from the depths of interplanetary space. Our knowledge of the universe is called into question by the discovery of these 300 mysterious objects. Do they represent the existence of hitherto undiscovered phenomena, undiscovered worlds just waiting to be discovered, or are they drifting artifacts from far-off star systems or fragments of old celestial bodies? Information sent from Voyager is usually quite easy to decode, but this data was jumbled. There weren't many answers, but there were plenty of questions. But then things became more bizarre. Voyager 1 itself appears to be undamaged and operating in excellent condition, despite the strangeness of the data that was relayed. The good news is that it was still able to communicate with Earth, and the signal was strong enough to transmit important data to NASA with little trouble. Curiously, the study found that the spacecraft had not even entered a protective safe mode, which would have been the standard procedure if it had identified any threats, and that none of its fault prevention mechanisms had been activated. Therefore, it was evident that Voyager was not actually being attacked. However, what might be causing the telemetry data to seem erroneous or jumbled? Were high-energy particles or radiation or other cosmic phenomena interfering with it? Or was there a completely unidentified phenomenon at work? Our knowledge of space and interplanetary communication would be called into question if the latter were true. But only by carefully examining a wide range of possible causes could we be certain. The spacecraft systems were thoroughly analyzed by the NASA research team, taking into account the effects of cosmic radiation on electronic components and the potential for temperature variations to compromise the integrity of its delicate equipment. The only issue was that it wasn't actually in the region where the natural hurdles were concentrated enough to even be a threat. It was plausible that something was happening just before Voyager struck the heliosphere and the obstacles caused the data to be jumbled. The scientists also examined the complexities of Voyager 1's communication systems, looking at possible signal distortions brought on by interference from cosmic noise or even minute changes in the spacecraft's trajectory. The team's quest for solutions prompted a careful examination of all relevant variables. In their thorough analysis of the spacecraft systems, they took into account the effects of cosmic radiation on electronic parts as well as the potential for temperature variations to compromise the stability of its delicate equipment. Even while it may seem like a checklist, there is a lot of work involved, and the study took weeks. To determine the underlying source of the odd telemetry anomalies, the team used sophisticated data processing methods, created creative algorithms, and ran multiple scenarios. This was the only way they could determine what might be causing the problems at that point. That effort wasn't in vain. The clarity and dependability of the data coming in from the deep regions of interstellar space were ultimately restored by scientists and engineers after months of getting jumbled data from the probe. An unexpected source, a dormant onboard computer, was identified as the Attitude Articulation and Control System (ACS) of Voyager 1 as the primary cause of the issue. You may be asking how problems may arise from something that isn't even meant to work. According to NASA officials, the transmitted data was corrupted because the ACS mysteriously began using a computer that had not been used for years. However, the remaining spacecraft stayed in operation and carried on with its data collecting without any problems. As soon as engineers identified the problem's origin, they came up with a solution. They instructed Voyager 1's ACS to switch to the appropriate computer so that the telemetry data could be transmitted. Due to the considerable time delay brought on by the great distance between Earth and Voyager 1, radio signals take about 22 hours to travel back and forth. This fix, albeit being relatively low risk, needed a great deal of patience. Extreme cooperation was required for the troubleshooting procedure, but there was just one issue. Because Voyager 1 had been in perfect operating order for decades, they had to comb through multiple manuals from the 1970s before they could begin troubleshooting. And that's exactly what they did. After careful investigation, they found that resetting the data transmission system was an easy and low-risk way to solve the issue. Without affecting any other components of the spacecraft, they managed to resolve the problem. Voyager 1's communication line was successfully restored thanks in large part to the engineers' skill and commitment. Their efforts demonstrated how crucial it is to use historical knowledge in conjunction with current technology to overcome obstacles in space travel. Engineers believe a malfunctioning command from another onboard system caused Voyager 1 to deviate and use the non-functional computer. According to this theory, there may be a fundamental problem with the complex computer system of the spacecraft. Mission managers are cautiously optimistic despite the worry, stressing that there is no serious threat to Voyager's long-term survival from the mishap. In fact, as soon as the proper computers were back online, Voyager quickly overcame the heliopause glitch and continued its journey. The heliopause, the line separating the furthest regions of our solar system, was therefore reached by Voyager 1, making history. It denotes the boundary of the heliosphere, the area affected by the Sun's magnetic field and energetic particles, and is situated where the Sun's solar wind meets the interstellar medium. The heliopause is situated at a considerable distance from our star, to put it mildly, at about 123 astronomical units, or an astounding 11 billion miles. The heliopause is distinct. The interstellar gas wind, which is brought on by the Sun's travel across space, can induce variations in its shape. The outermost part of the heliosphere is shaped by the magnetic bubble or foam that the Sun forms inside this limit as it moves. The heliopause's complex structure and behavior are influenced by this magnetic foam. A number of events occurred as Voyager 1 and subsequent spacecraft passed through the heliopause. First, as the spacecraft passes outside the direct emission of the Sun, the temperature of the solar wind-charged particles significantly decreased. Most spacecraft would be rendered worthless by this alone, yet Voyager continued to move forward at full speed even though it wasn't designed to travel that far. Along with a significant increase in galactic cosmic rays, which are high-energy particles from distant cosmic sources that become more prominent beyond the heliopause but begin to appear just before it, there was also a change in the direction of the magnetic field, reflecting the altered influence of interstellar magnetic forces. As the first of the twin spacecraft to achieve this significant milestone, Voyager 1 illuminated the enigmatic shift from the Sun's light to deep space and gave humanity its first look into the unexplored regions beyond the heliopause. Similar to its predecessor, Voyager 2 crossed the heliopause and entered interstellar space in November 2018. This momentous accomplishment opened a new chapter in our knowledge of the line separating the interstellar medium from the Sun's world. By comparing and contrasting the findings made by both spacecraft, scientists were able to gain a deeper understanding of the celestial frontier overall, thanks to Voyager 2's contact with the heliopause. Voyager 2 produced fascinating discoveries as it traveled outside the heliopause, expanding our understanding of this uncharted area. One noteworthy finding was the dramatic rise in low-energy ion intensity, which was caused by escaping the Sun's direct emission impact. In fact, Voyager 2 saw a concurrent rise in cosmic ray intensity, which are high-energy particles from far-off cosmic sources. Voyager 2 faced a different situation than Voyager 1, which had antecedent events before leaving the heliosphere. Voyager 2 revealed the existence of a separate boundary layer immediately beyond the heliopause, rather than precursor events. Low-energy particles streamed outward along the Milky Way in this boundary layer, revealing interesting details of the complex dynamics at the barrier between the interstellar medium and our solar system. Overall, this surprising discovery brought to light the intricacy of the interstellar barrier and the possibility that it would be difficult to foresee if two spacecraft that appeared to be identical had quite different experiences. It's difficult to predict how other spacecraft passing through the same region might fare. Given the possibility of it all being wasted, will NASA really be prepared to risk billions of dollars and put everything on the line? Even though the heliosphere is incredibly powerful, NASA is still interested in learning everything it can about it and beyond. All the information will be collected by the Interstellar Probe. An ambitious NASA space probe proposal called the Interstellar Probe seeks to go beyond what the Voyager spacecraft accomplished. This historic mission, which was first proposed by NASA's Applied Physics Laboratory in 2018, calls for the probe to be launched between 2036 and 2041 and set out on a multi-decade trip that will take it hundreds of astronomical units from Earth. The necessity to collect detailed measurements and information about the conditions that exist across the heliosphere and heliosheath is at the core of the Interstellar Probe's mission. Indeed, there is a distinction between the two. The heliosphere is the area that is affected by the Sun's solar wind, whereas the heliosheath is the outermost layer of the charged particle bubble that surrounds the Sun. The interplanetary probe is a major advancement in interplanetary exploration thanks to its use of cutting-edge modern technologies.